All right, let's find the signed volume underneath this function over the rectangular region with corners at 1 comma 0 and 2 comma pi. So we saw in the last video that signed volume could be accomplished by a double integral, and our shorthand notation was this. All right, where R meant our region, whatever that happened to be, and dA could be either dx dy or dy dx, whichever one is going to be more convenient for us. All right, so let's go ahead and draw our region. It says it's the rectangular region with corners at 1 comma 0 and 2 comma pi. All right, so I'm going to draw that. So 1 comma 0 would be this point here, and then 2 comma pi. I don't know, let's put that up here. 2 comma pi. All right, so the rectangular region with those 2 points as corners, we can go ahead and draw that. So this is our region R. So we can imagine whatever this surface is, it's floating up above my page, and we're trying to find the volume that's trapped just over this rectangular region that I've drawn. All right, so let's go ahead and set up our double integral. I haven't decided yet if I'm going to integrate first with respect to x or y, so I'm leaving my limits blank for just a second. Let's write our function in here. And we really need to decide whether we want dy dx or dx dy. All right, if I try to integrate with respect to y, I've got a y inside the sign and a y out front. And we know we don't have a product rule for integrals. We would possibly have to integrate that by parts, and I'm not looking forward to doing that. So I'm going to try to integrate with respect to x first and see what happens. So I'm going to say dx dy. So that means I need my x limits on the inside integral, so from 1 to 2. And then my y limits on the outer integral, y looks like it's going from 0 to pi. All right, so I'm going to come over in my scratch work over here off to the side and see about integrating y times sine xy with respect to x. For that, I'm going to need a u substitution because I have a coefficient on my x inside the parentheses. So I'm going to let u equal xy, and then du is going to be equal to y dx. Remember, we're treating y as a constant. All right, so actually that y being an integral is kind of helpful because the y and the dx together are going to make my du. So this would be the integral of sine u du. That's really easy, right? Negative cosine u, which is going to be negative cosine xy. All right, so that's my antiderivative. So I've got over here on the left, the 0 to pi integral is just hanging on until I'm done. I've got negative cosine xy. Evaluate that from 1 to 2. dy hanging out with like the bookends with its integral from 0 to pi. All right, so we integrated with respect to x, so I'm going to plug in a 2. So I've got integral from 0 to pi, negative cosine 2y minus a negative cosine of 1y, all of that dy. All right, so we know that the antiderivative of cosine y is just sine y. I've got cosine 2y. We actually need a little u substitution to be able to evaluate that integral. So let's make some room over on our scratchwork side of the slide. And I'm going to integrate cosine 2y. I know I've got a negative sign on there, but we'll just kind of hold on to that for later. And I'm going to let u equal the inside function, 2y. So du is 2 dy. So I need a 2 inside my integral to go along with the dy to give me du. If I do that, I need a 1/2 to compensate for it outside. So I get 1/2 integral cosine u du. Antiderivative of cosine is sine, so I get 1/2 sine u, which was 2y. All right, so my antiderivative of cosine 2y is 1/2 sine 2y. So let's continue our work over here. I've got negative antiderivative of cosine 2y. I just figured out was 1/2 sine 2y. Antiderivative of cosine is sine, so sine y. And all of that we're going to evaluate from 0 to pi. Again, I need more room. Let's get rid of our scratch work over here. And let's plug in pi. Minus, plug in 0. All right, so if you think about 2 pi, pi, and 0, we've got to find the sign of all of those spots on the unit circle. But if I think about my unit circle, let's see, 0, pi, and 2 pi, all three of those have the same sign value. They all have a value of 0. So I've got 0, 0, 0, and 0. Everything in this entire integral ends up evaluating to 0. But I thought we were calculating the volume underneath the surface. What is going on here? So here I have graphed our function y times sine xy, and I have it zoomed into about the area that we need. Remember, we were going from x equals 1 to 2, and I've got the red x-axis going out to 2, and then y was going from 0 to pi, which is about the part of the y-axis that I've got here. And remember that the double integral is going to treat volume that's above the xy plane as positive volume and volume that's below the xy plane as negative volume. So this bit of the graph that swoops down below the xy plane has exactly enough negative volume to cancel out the positive volume that you had above the xy plane. So this is what we mean by sign volume. It's that the negative volume, if there is any, has a chance to sort of cancel out any positive volume. So we're just going to keep that in mind when we do these calculations, that sometimes you might have negative bits canceling out positive bits. So we'll do a few more examples of volume trapped underneath the surface when we get together in class.